So next, we are going to talk about this, the pipelining. We are going to talk about the pipelining process. So in pipelining, as we have seen that, there are different phases of your multi-cycle. One is your instruction fetching, instruction decoding, instruction execution, your memory access, and write back. So in instruction fetching, we have find that some of the components which we are using, your program counter as well as the instruction memory unit, instruction memory. For instruction decoding, we use the register file. We use the register file as well as your signed extender units. In the execution, it use the arithmetic and logic unit. For memory access, we use the memory called the data memory, the data memory, the data memory. And in write back, again we use the functional unit, your file, register file. Okay. So let us go and discuss about this pipelining basically. So for this topic, we are going to cover this, what is overview of pipelining, and there are certain hazards, the difficulties while executing the instructions by following the pipelining process. One is your structural hazard, that is the hardware arrangement hazards, and your control structural hazard, and your data hazard, and your control hazards, and your summary of your these solutions. For this, you can go through the first textbook, the computer organization and design, go through chapter 6, where enhancing the performance of your pipelining. And from the second textbook, we can go with the appendix C, where the pipelining basics and the intermediate concepts are covered. So in the overview of this, the definition and the practical observation about this pipelining is, you just observe this, the pipelining, here you can find the instruction fetching stage, instruction decode, your execution stage, your memory access stage, or your the write back stage. So if you recall that in pipelining, the implementation technique in which multiple instructions are overlapped in execution, much like the assembly lines only. So the formal definition for this pipelining, it says that the pipeline process is comprised of your sequential linear list of segments. So these are segment 1, segment 2, segment 3, segment 4, and segment 5, where each segment performs one computational task or your group of tasks. So the observation in this pipelining is, there are three things that one must observe about the pipelining. First, the work is divided up into the pieces that more or less fit into a segment. Okay, so that is allotted for them. So what is that? If an instruction is given as an input to your the execution phase, then the first one, it is going to enter into the first stage. The first stage is the instruction fetching stage. So as soon as its first stage is over, this instruction, it may goes into the next stage, instruction decoding. When it goes to instruction decoding, during that time, the remaining phases during instruction fetching, this phase is idle. This phase is also idle. This phase is also idle. This phase is also idle. Like the execution, your memory access, or your write back. These phases are idle because the hardware which is there in these phases, they are idle. So in pipelining says that if the first instruction is utilizing the hardware part of your first stage, then any other instructions, they may use these things, but in a sequence one. So first instruction 1 goes, then instruction 2 goes, and so and so. The second, the work partition must each take about the same time, to complete. So otherwise, the longest partition required time is suppose T would hold up the pipeline, and every segment hold would have to take time T to complete its work. So for fast segments, this would mean much idle time. Third one is, in order for the pipeline to work smoothly, there must be few exceptions and hazards that cause error or the delay within the pipeline. Otherwise, the instruction will have to be reloaded and the pipeline restarted with the same instruction that caused the exceptions. So then another important part in this pipelining is your response time. Okay. So it is easily verified that the response time for any instruction that takes three segments. One is your, the instruction decoding, your execution, and your, the write back. Instruction fetching, decoding, and your execution. So these are very important phases, are very important segments in the pipelining. So this response time for any instruction that takes three segments, that must be three times the response time for any segment which is provided that pipeline was full when the instruction was loaded into the pipeline. If there are n segments, in our case 5 segments are there, but sometimes if we say if there are n segments, okay, why? Because we have seen that ALU operations will take only 4 cycles. Your memory operations will take in memory operation, if it is load, then it takes 5 cycles. If it is store, then it takes the 4 cycles. For branch, it takes 4 cycles. So segments are different. So if an n segment pipeline is empty before an instruction starts, then n plus n minus 1 cycles or segments of your pipeline are required to execute the instruction, because it takes n cycles to fill the pipe. Takes right. So in this the concept of your pipelining, as we just saw, the response time, it is easily verified, as we said this thing. So then comes to the next important part, that note that we just used the term cycle and segment. This is very important for your assignment as well as examination. So we use cycle or segment simultaneously. Cycle or the segments synonymously. So in the type of your pipelining that we'll study in this section upcoming, each segment takes 1 cycle. So your instruction fetching segment takes 1 cycle 1. Instruction decoding segment takes another cycle. Instruction execution segment takes another cycle, and so on, so up to your memory and your write back also takes the different cycles. So thus the n segment pipeline takes a minimum time of your n cycles to execute one instruction. So to do this, the work should be partitioned, as we just seen in previous examples also. So we just designed a multi-cycle data path that is based on the assumption that the computational work associated with the execution of an instruction that could be partitioned into 5 steps, that is instruction fetching, decoding, execution, memory, and your write back. So here you just remember instruction fetching means fetching from the instruction memory. Instruction decoding, it is decoding instruction as well as reading the register memory. So register file is accessing here. In execution, the operations are it calculates the address. So here the ALU functional unit is accessing, whereas in memory instruction, it access and operand into the data memory. Here is your instruction memory, here is the data memory, where write back the result will be right into register. So register file is accessed here. So these are some basic concepts. Now let us get into the what is pipelining and what is non-pipelining for executing the instructions. This is very important for your assignment as well as your the instruction. I mean the assignments and your examination part also. This slide is very important. Listen carefully. So let us see the difference between pipelining and your non-pipelining part. Okay, for let us talk about the non-pipelining. For simplicity, we assume all the instructions need 5 changes. So the instructions, it may be your arithmetic and logic unit instructions, or your memory operation instructions, or your branch instructions. Anything that you can, any class of instruction that you can take, we assume that every class of instructions they are taking 5 stages. What are the 5 stages? The 5 stages, as we know, that instruction fetching, decoding, execution, memory, and write back. So without pipelining, that means no overlapping is there. That means if there is, they consider this bar as your cycles, how many cycles it takes, and consider there are 3 instructions: instruction 1, instruction 2, and instruction 3. So without pipelining, the first instruction when it is going to execute in the cycle 1, it is going to fetch the instruction. In the cycle 2, it is going to decode the instruction. So when this instruction 1 is in the decode phase, though this phase is idle and these phases are also idle, they are not utilizing. This phase means these segments are idle, means the functional units are idle. When first it entered into the first segment in the first cycle, that is instruction fetching, it is going to utilize the program counter and your instruction memory unit, program counter, instruction memory unit, and the adder function, which is adding your +4 bytes to your program counter. Okay, so these 3 units are utilized, but during that time your the instruction decoding phase, execution phase, and those are idle, but still we are following the non-pipelining, so it is not going to be used by any other thing. Correct? So then when it is moving to next phase from instruction fetch to decode phase, then in the instruction decoding, the register file read, the register file, functional unit will be used. Then it moves to the next stage. In the execution, it uses the ALU unit for doing the arithmetic and logic operations. Then it moves to next stage, that memory access. In that memory access, if this instruction requires, then the memory read or write operation will be taken. Here this memory is your data memory, and then it goes to your write back. Here the register file is used to write the data back. So once this the first instruction is complete, then the second instruction starts at the next cycle. Again starts with instruction fetching, decoding, execution, and once second instruction is finished, then it goes for the next. So how many cycles it takes for 5, for the 5 stages of your instruction assumption? It takes 3 instructions, it takes 15 cycles. 3 instructions takes 15 cycles. That means every instruction is taking T cycles. So there are T cycles. If there are 3 instructions, means it is multiplied with T cycles. So here T means T is taking your 5 cycles to complete the instruction. So it is giving that 3 into your 5. The 15 cycles are required in non-pipelining. But if it is a pipelining, with the pipeline, then the average, the performance of your the architecture, it gives that there are 15 cycles. So the CPI, which we have done this in the performance evaluation, that cycles per instruction, total number of cycles are 15 for these many instruction. So 15 cycles divided by 3, it is giving 5 cycles. The average 5 cycles are taken. Okay. So now with pipelining, same instruction set with pipelining, if you take first instruction is given to the first stage. So in the first stage, you are having the program counter, PC, and your memory, instruction memory. You can write as your instruction memory. Okay. And this is your internal buffer, the inter buffer. So program counter issues the address to your instruction memory. So the instruction fetch and store into the inter buffer. Okay. So in the first cycle, the first instruction one is entered into your first stage, right? So then in the second stage, it is going to the next level, that is the instruction decoding phase. This is instruction fetching phase. It goes to your instruction decode phase. When it is the first instruction one is going to the instruction decode phase, here the register file is there. Then when this is instruction is going, then this program counter and memory unit become idle. Okay. So in that, the second functional unit, so the first instruction is in instruction decode. So your first functional unit, the instruction fetch stage, at this segment functional units are idle. So second instruction will be given as an input to this, right? So then if you see that in IF, the first instruction, let us say instruction one is given as an input to the first stage in cycle 1. Then in cycle 2, it is moved, the instruction 1 is moved. So then the resources which are there here, program counter and your instruction memory become idle. So instruction 1 is using the register file here, in the second cycle. So when in the cycle 1, these become the idle, so the instruction 2 will be given as an input to here. So for in the second cycle, instruction 1 is utilizing the second segment, that instruction decoding, and your instruction 2 is utilizing the hardware part of your first cycle. So that is instruction fetching stage. So in the third cycle, first instruction is utilizing the third segment of your multi-cycle data path, that is using the ALU unit, whereas your second instruction, it is using the register file, and the third instruction, it is using the first one, that is your program counter part. Okay. In the next cycle, in the fourth cycle, your first instruction is utilizing the segment of your memory instruction, and then your second instruction utilize the third segment, because it completed your instruction fetching, instruction decoding, it entered into your execution, and in the third instruction, it will utilize the instruction decoding. So you can see in every segment, you can see in the first segment, first instruction is executing. In the second cycle, 2 instructions are executing. First instruction is instruction decoding phase. Second one is instruction fetching phase. In the third cycle, first instruction is in third segment, execution segment. Second one is in instruction decoding. So it is a pipelining process. So instruction 1, instruction 2, instruction 3, they are in the pipeline. They are giving as an input to the instructions. They are giving as an input to your multi-cycle data path. So the propagation is going on from instruction fetching, instruction decoding, instruction execution, instruction memory. Then it goes to the last phase, your the write back. So the propagation, when instruction 1 is here, they are in line. When instruction 1 is here, then instruction 2 will be here. When instruction 1 is in here, then instruction 2 will be here, and instruction 3 comes here. So this process is continuous. So with this, if you see, the same 3 instructions take 15 cycles to execute in non-pipelining, whereas in pipelining it takes only the 7 cycles. 7 cycles. So with pipelining, 3 instruction takes only the 7 cycles. Takes only the 7 cycles. So what is the ideal pipelining performance means? Without pipelining, as we observe, we assume that instruction execution takes 3 times, like 5 cycles for each instruction, 3 times. So single instruction latency takes 3 times, 5 cycles. So what is the throughput? One time it is giving only 1 cycle, 1 instruction is executed with the 5 cycles. So the throughput of that is 1 by 3. So if there are m instructions, in our case 3 instructions are there, so the 3 instruction latency gives that 3 into 5, that is 15. But whereas in throughput it is given 1 by t only. So if the execution, this slide is very important for your assignment, for calculation also. Remember, for non-pipelining, the instruction latency is m into 2 and the throughput is 1 divided by t, where t is the instruction latency. If the execution is broken into n-stage pipeline, that means pipelining process is there, then ideally a new instruction finishes each cycle. Ideally, a new instruction finishes each cycle, as we saw that in each cycle. In the first cycle, only 1 instruction finish. In the second cycle, 2 instructions are finishing. In third cycle, 3 instructions are finishing. In fourth instruction, all the 3 instructions are finishing. So it takes, if you count this, then it gives the end stage pipeline. Ideally, a new instruction finishes each cycle. Okay, so the time for each stage is calculated as small time for each stage. It may be your instruction fetching stage. At that time, the time will be taken by the segment is the total time which is required for your instruction divided by the number of stages. Suppose for addition operation, it takes the addition operation, it takes 4 cycles, as we saw in previous one, 4 cycles. And how many stages it is going to complete? The total number of stages are 5 stages. If you are assuming 5 stages, then this is the time which is required for addition operation. If it is memory, then it requires 5. So that is for each, the time for each stage is calculated as your t divided by t is equal to the total latency time, instruction latency time divided by number of stages. How many stages are given? So then the throughput will be calculated for each stage. For each stage is 1 divided by t. Whereas here, for throughput will be calculated for entire stage, entire latency time. So for m instruction latency, it is calculated as the m instruction latency, the number of instructions multiplied by the instruction latency. So here, number of instruction multiplied with each stage latency, that is t. So that can be written as your m multiplied with your t. Small t means small t is your t divided by n. So t divided by n, that is nothing but your m multiplied by t divided by your n. So this m multiplied by t is the ideal pipeline performance, which is always equal to always less than your the non-pipelining part. So, but in this case, in end-stage pipelining, the CPI, cycles per instruction with pipelining, is 1. So to do this, now in this case, if you say that, we have seen there are 5 stages, right? First stage, second stage, let me just recall, third stage, your fourth stage, and your fifth stage. So we have three instructions. Instruction 1, instruction 2, instruction 3. Three instructions are there. Then in pipelining, how it is using, this is your instruction fetching, instruction decoding, instruction execution, instruction memory access, instruction write back segments. Okay, or stages we can call. Okay, so first instruction 1 is getting into the instruction fetching. So instruction 1, the first cycle. In the second cycle, your instruction 1 is going to your instruction decoding phase. So where this instruction fetching can be utilized by your instruction 2. Okay, in the second cycle. In the third cycle, the instruction 1, this instruction 1 is propagated, get into the execution stage. So then this ID will be free, so that will be given to your instruction 2. Those units will be used by instruction 2. So here when this one is moved from here to here, then these are idle. So instruction fetching stage will be given to instruction 3. In the next fourth cycle, it will be goes to your memory access stage. Then your 2 will go here, then it become idle. Then 3 will be enter here, that instruction decoding. Now there will be some hazards. So for this operation, like this in the propagation part, there is a possibility that multiple instructions, they may have some difficulties. What are those difficulties? We call those difficulties as your hazards. So in pipeline processor have several problems associated with controlling smooth, efficient execution of your instructions and the pipeline. So the problems are generally called hazards, and that include three types of hazards. One is your structural hazards, another one is your data hazards, another one is your control hazards. There will be three hazards are there. Structural hazards means these structural hazards occurs when different instructions collide while trying to access the same piece of your hardware in the same segment of your pipeline. That is structural hazard. So this such structural hazards type of your hazard can be elevated by having redundant hardware for the segments wherein the collision occurs. So occasionally it is possible to insert stalls, or we call bubbles. Insert stalls or bubbles, or reorder the instructions to omit this type of the dependencies, the hardware dependencies. So if multiple instructions, they are trying to access the same hardware, watch hardware part, they may, suppose we have the instruction 1 and instruction 2, if both are required the memory access, suppose memory access or your register file, in that case you will find the structural hazards, because whether at the same time whether this memory unit has to perform read operation or write operation, so that's a problem, right? So then the data hazard, this data hazard occurs when the instructions depends on results. Instructions depends on result. Which result? Your ALU result. ALU results depends on the results of your previous instructions still in the pipeline. So which results has not yet been computed, So the simplest remedy for this data hazards are just inserting stalls or bubbles in the execution sequence, which reduce the pipelines the efficiency. So the solution to the data dependencies is twofold. That is, first one is one can forward the ALU result to write back or the data fetch stage. So this data hazard problem comes in the instruction decoding phase and your write back phase. Which one should be taken? The second, the selection instance, it is possible to restructure the code to eliminate some data dependencies. Third one is your control hazard. This control hazard comes because of your branch instructions. In the branch instructions, the branch target address which we calculated, that depends upon your Z flag register, that might not be ready in time for the branch to be taken. So which results in stalls in the pipeline that have to be inserted as a local wait event until the processing can resume after the branch target is executed. So control hazards can be mitigated through the accurate branch prediction, which is difficult by delaying the branch strategies. So let us see the structural hazard, how it happens. So when two different instructions want to use the same hardware resource in the same cycle, then the resource conflict will be there. If you see in this example, in the following example, we have four instructions. They are undergo through four different stages, like instruction fetching, decoding, execution, memory, write back, right? So let us consider at this cycle, this is cycle 1, cycle 2, cycle 3. At cycle 4, there are all the four instructions are there. So your first instruction is utilizing the memory, second instruction is utilizing the execution stage, and third instruction is using your data decoding, I mean the instruction decoding. Fourth one is in the instruction fetching. So all four segments or stages are there in the execution. So the first instruction fetch is utilizing your instruction fetch is utilizing with your instruction 4. Instruction the decode is utilizing by your instruction 3. Instruction 3, here is instruction 2 is utilizing the execution mode. Instruction 1 is utilizing the memory access mode. Okay, so IF, ID, your execution, and your memory. The memory. Now this, in this case, if you see, when the first instruction, the fourth instruction is in the first mode, it is instruction fetching. Instruction fetching, we know that from where the instruction is fetching, instruction fetching from your instruction memory, or fetching from your memory only, right? Whereas in your instruction 1 is in the instruction memory execution stage, where it is also accessing the memory. So in that case, instruction 1 and instruction 4, both the instructions are accessing the memory. In that case, in the instruction fetching, read operation will be there. In this after execution, it will go with your write control signal. So whether that instruction memory should go with your read operation and write operation. So there is a conflict. Okay, so that is instruction 1 and instruction 4 have two structural hazards at the memory. Okay, and you can see the same thing when the instruction 1 is in the last stage, write back stage, and your instruction 2 is in the instruction decoding. In both the case, in write back stage or in our instruction decoding, in both the cases, they use as the register file only. In the first case, when the instruction is in memory, they are using the memory access. In memory access conflict is there. When the instruction 1 is in write back and instruction 4 is in instruction decoding, then they both access the register file. So instruction 1 in the write back stage writes to the register, and instruction 4 ID stage reads the register. So both requiring the accessing register file. So that's a resource conflict. So we call this as your structural hazards. So what is the solution for structural hazard? Means you can separate the hardware resources. So for the first one, at cycle 4, if the first instruction, the memory is supposed separated, as we know that in the clock cycle edges, lower lower or falling rise means it is a read operation, and your rising edge means it is a write operation. So if you divide this memory into two different part, into first half cycle for read purpose and second half cycle for your write purpose, you can divide this and divide this memory into two part. One is the memory which is using at the instruction stage, that is for your use the instruction memory. As we saw in our previous lecture, there is the first stage memory is not same as the last stage memory, that is instruction memory, and the last stage memory you can write it as your the data memory. So if you divide this memory like data memory and instruction memory, so that resource separating the hardware, then the structural hazard will be resolved. Structural hazard will be resolved. So for the contention, of your memory stage and your instruction fetching stage, if instruction fetching stage only use the read instructions and the memory instruction stage only access the reader writes data, then we can then separate the memory for instructions and your data. So that is the first memory which we are using in our example. The first memory which we are using, that is instruction memory, and second last one which we are using in the write back in the memory access which we are using, that is your data memory. So this structural hazard is the one of the motivation of using separate instruction memory and your data memory. So this, for this instruction memory and data memory, the L1 caches will be used. We will discuss this L1 caches when we talk about the caches. So this L1 cache is divided into your instruction cache memory and your data cache memory, where in the instruction cache memory can hold the instructions and data cache memory holds the data. So this instruction cache memory will be present in the instruction fetching, and your data cache will be used in the memory stage. Right. So with this, the structural hazard can be solved in another way. The structural solution lets this access to the same hardware component happen at a different part of your cycle. So for that, the continent of your the second case, the second hazard which we found at the register file stage, right? In this stage, the instruction one is also writing into the writes to the register file, and instruction 4 is reading from the register file. To follow this solution, this register write back stage access registers at the first half. As we said, for write back, it takes the first cycle, and the second cycle is used for your reading purpose. So write back takes the access register at the first half of your cycle, that is the falling edge of your cycle, and the ID in instruction decoding read will be there, so that the rises at the second half of your cycle, that is your rising edge of your cycle. So alternatively, we can also make a stage multi-cycle, and they let the conflict access happen at a different cycles. So this situation can be accommodate more than two conflicts. In this case, the hazards removed as the write back happens at the first half of your cycle, and while the ID happens at the second half of your cycle, so that in the first half write operation will be taken, in the second half the raising one it takes. So at this cycle, the same register file is accessing, but the first half of your cycle, the first instruction is going to write into the register. In the second half of the cycle, at the fifth cycle, the fourth instruction will read the data. That will reduce the structural hazard. So with this, I would like to stop this session.